My name is Jean-Christophe Calvey. This presentation is about LDAS-Monde. LDAS-Monde is a powerful tool to monitor vegetation. It is based on the ISBA land surface model within the Surface modeling platform of Météo France. LDAS-Monde is able to sequentially assimilate leaf area index alone or together with surface soil moisture. And a unique capability of this system is that even if LAI is assimilated alone, the root zone soil moisture can be analyzed. Also, LDAS-Monde is able to assimilate snow water equivalent products. Sequential assimilation of LAI is possible because phenology in the ISBA land surface model is completely driven by photosynthesis, and as a result, LAI is very flexible. LDAS-Monde is able to work at a global scale at a spatial resolution of 25 kilometers, but it can also be implemented over Western Europe, for example, at a spatial resolution of 1.3 kilometers, thanks to the atmospheric variables coming from the AROM numerical weather prediction model. The current evolution of the system is the following. New versions of the ISBA land surface model are being used together with a new version of the Kalman filter. And also we are working on new observation operators to assimilate new satellite-derived observations. Envisaged applications are generation of real-time LAI for NWP, clay shrink swell monitoring, initialization of seasonal prediction models, enhanced dry deposition forecasts, and root zone soil moisture products. Thank you for your attention.
Hi everyone, my name is Nina Rout and I will be introducing the ORCHIDEE team. We are a very active group, mainly based at LSE in France, although we do have some members internationally. Hopefully you'll get a chance to meet most of us over the next few days. The ORCHIDEE team's main goal is to use data simulation to improve the ORCHIDEE land surface model. We have a bespoke tool written in Python which allows us to conduct our experiments. We mainly focus on optimizing internal model parameters by simulating data either from individual locations or over multiple sites. We also have a possibility to assimilate multiple data streams. In addition, we have a dedicated website which I invite you all to check out for further description of our tools, tutorials on how to use it, as well as a full list of our results and publications. Over the last 25 years, we have assimilated a large range of different data streams, starting with in situ sites like FluxNet sites, and then moving to satellite retrievals like NDVI, FAPAR. We've also been looking at other indicators of GPP, such as SIF and COS, and we're looking more towards including data from other terrestrial data streams, such as soil moisture and land surface temperature, given the strong coupling between the carbon, energy, and water cycles. In addition to assimilating many different data streams, we've published studies looking at the best methods behind the data simulation. So we've compared optimization techniques, as well as how best to assimilate multiple data streams, so stepwise or simultaneous. And finally, a brief word on our perspectives. We are looking at new ways for data simulation. So we've been developing the adjoint to help with the same methods, as well as looking at history matching, which uses emulators of models. We've been looking at novel data streams to assimilate, as well as other terrestrial carbon cycles they can constrain. And finally, we are working towards global optimizations using multiple data streams to exploit the expertise we have acquired over all of the years. Thank you very much.
Hello, my name is Freikle, and I have a brief update on land data simulation activities at the NASA Global Modeling and Assimilation Office. First and foremost, we're working on the SMAP Level 4 soil moisture product, which last year we upgraded to version 6, where we used iMerge, satellite engaged precipitation, to force the land surface moving away from the CPC unified gauge only precipitation product. And this map here shows the skill difference in surface soil moisture anomaly skill, and you can see that with the iMerge precipitation, we're doing considerably better, primarily in the southern hemisphere. So that's encouraging. And the same iMerge precipitation we're also going to use in our forthcoming reanalysis of the 21st century, R21C, with production starting soon. And using iMerge here eliminates a low bias and the discontinuities. This is for South America, step change here. That's seen in AMERA2 precipitation and consequently, of course, land surface hydrology. Unfortunately, we still don't have a land surface analysis in R21C. To make that happen for AMERA3, we included the SMAP radiance assimilation into our atmospheric data assimilation system, or ADAS. So the control here is a half-degree version of the ADAS, and the experiment SMAP DA includes the weakly coupled SMAP radiance assimilation. And the top panel shows that the SMAP assimilation improves the scale of specific humidity at 2-meter screen level versus station observations. The bottom panel shows the same for the maximum daily air temperature. These improvements extend into the lower troposphere, which isn't shown, and also persist into 5-day forecasts. Thank you for listening.
Hi, I'm Pete Weston from ECMWF, and I'm going to talk to you today about our land data assimilation system. Currently, we have a system made up of different tasks which analyze the different variables separately. This includes 2D optimal interpolation methods to analyze the 2-meter temperature and 2-meter relative humidity. We also use a 2D OI for the snow depth, and then we assimilate the 2D temperature and relative humidity analysis as pseudo observations into our soil moisture simplified extended Kalman filter. In this system, we use EDA Jacobians, but we still just use climatological background errors. And then finally, we have a 1D OI to analyze the soil and snow temperature. In the future, we hope to move to a more unified ensemble-based system. This will be easier to maintain and develop. It should provide a consistent multivariate land surface analysis, which will hopefully improve the quality of our Earth system analyses and forecasts. We'll use flow-dependent perturbations and background errors, and will again hopefully lead to better exploitation of observations over land, snow, and sea ice. In terms of the coupling, I'll show a couple of simplified schematics here, just showing our land atmosphere coupling. So we have a coupled model, and then this feeds into a coupled trajectory within our analysis, but then the actual assimilation is done completely separately. So here on the left, you can see the land data assimilation system, and on the right, the atmospheric 4D VAR. And currently, it's only the atmospheric 4D VAR which feeds into the different trajectories within each outer loop of our assimilation system. The land analysis is only fed into the next model cycle, and that's why this is a weak assimilation coupling. In the future, we hope to move to a more strongly coupled assimilation system. So the main difference is that the land analysis is now fed into each different trajectory within the different outer loops, allowing the atmosphere and the land to update simultaneously, and hopefully lead to some benefits. Thank you for listening.
Hello, I'm Sujay Kumar from the Hydrological Sciences Lab at NASA Goddard Space Flight Center. I will briefly describe the Land DA activities with the NASA Land Information System, or LIS, and our priorities going forward. Very broadly, LIS is an environment that integrates land and hydrology models with remote sensing data and assimilation tools. LIS has historically been used to support a variety of activities, including mission development, land hydrology research, applied science, and operational environments. This chart shows a timeline of major LIS activities starting in 2002. As you can see, LIS has been used in a variety of end-use environments and has been used to transition the use of remote sensing data for both univariate and multivariate application. LIS currently supports the assimilation of a large number of remote sensing products from various sensors as shown here. Using LIS, the assimilation of soil moisture, snow, skin temperature, terrestrial water storage, vegetation, albedo datasets, both concurrently and separately has been demonstrated. The priority areas for LIS going forward are listed here. There is a big emphasis on improving the utilization of information from observations with both data-driven and forward modeling approaches. Recent studies have also shown that multivariate DA is not only important, but also necessary for capturing the cross connection between Earth system processes and human impacts. This is another important focus area for LIS. Another priority is to enable the system to take advantage of data from upcoming missions such as SWAT and NISAR. There are also ongoing efforts to exploit data from commercial platforms and future adaptive type of missions. We are also focused on exploiting opportunities to showcase value for mission data through operational hydrology and more land-focused water resources and agricultural management applications, in addition to NWP. Finally, we think modernization of the software by enabling containerization and virtual executions on cloud environments is a future, and it's needed to enhance the accessibility of land remote sensing and data assimilation efforts. Thank you.
So today I would like to talk about the Land Surface Data Assimilation System at Environment and Climate Change Canada, and in particular the CaLDAS, what we refer to as the Canadian Land Data Assimilation System. So CaLDAS really has two core objectives, which are to provide the best estimate of the land surface state. This includes the surface temperature, soil moisture, snow, and also clearly to provide the initial conditions to the various environmental prediction systems that you can see listed here on the top. The three key components of CaLDAS, we have the observations, the simulation methodology, and the first guess modeling. So in terms of the observations, you can see in black we have the traditional surface-based observations, temperature and dew point temperature at screen level. We have the in-situ snow depth observations. And then we have the more recent innovations that we have incorporated into CaLDAS, which are shown in red here, which are based on the space-based remote sensing for the soil moisture with SMOS and SMAP, the skin temperature retrievals, the IMS for snow, and then the ground-based radars and iMerge for precipitation analysis. The simulation methodology in CaLDAS is based on the ensemble Kalman filter. And then we have the first guess modeling, which is really driven. We have an offline driver for our land surface modeling, which is referred to as a surface prediction system, which is fed with atmospheric forcing and geophysical fields. So if we go ahead and look at the details of the surface prediction system, really at the heart of CaLDAS it's an offline or external system. So we run the 2D land surface model typically at higher resolutions than the atmospheric forcing, which comes from a lower resolution 3D atmospheric model. And really the reason we do this is because it gives us the ability to run the land surface at a higher resolution at a much reduced cost when compared to running the 3D atmospheric model. So I just want to finish up here with talking about a brief overview of one of the prediction systems which really incorporates many of the recent innovations in terms of the land surface modeling and remote sensing observations. So we're talking here about the National Surface and River Prediction System. And it's really the analysis component. CaLDAS is really the analysis component of the system, which provides a forecast of the land surface and also the hydrology, as you can see on the right here. Thank you.
Hello, I'm Andy Fox. I'm going to provide a very quick update on Land DA at the Joint Centre for Satellite Data Assimilation. This work involves a lot of contributors. I will name check them on the slides as we go. The JCSDA is a multi-agency research centre that partners with NOAA, NASA, Navy and the Air Force and works very closely with NCAR and the Met Office to improve and accelerate the use of satellite data in environmental modelling systems through robust data infrastructure and open source software. The main example of which is the Joint Effort for Data Assimilation Integration, or JEDI, which is a generic portable model-agnostic data assimilation system. We currently have two Land DA applications using JEDI. The first is a Land DA system for the Unified Forecast System. The second is a Snow DA system for WRF Hydro, which is a continental scale hydrology model. The UFS work is being led by Clara, and this will become the operational system used by NOAA. It uses the FEC JEDI interface, so it's closely coupled with the atmosphere model, although they have a workflow for both offline and online capabilities. Snow Depth DA has been implemented as a special case of LTKF. and work is underway in testing the simulation of SMAP soil moisture. The Wolf Hydro application has been developed in close collaboration with scientists at NCAR with the goal to assimilate both SWE and snow depths to improve forecasts of melt-driven streamflow. We've developed an interface between Wolf Hydro and JEDI and put together a workflow with HFX and LTKFOI capabilities. And here are some preliminary results showing O-B for observations and the resultant increments across our test domain in Western Colorado. Our future plans are closely tied to JEDI developments as a whole, but in the short term, we want to work on adding the ability to assimilate brightness temperature observations of soil moisture and improve our bias correction capabilities. Thank you for listening, and please contact me directly if you have any further questions.
Hi, my name is Brett Rask. I'm Associate Scientist at NCAR, and I work within the Data Assimilation Research section. Today I'll talk about Ensemble DA with the Community Land Model. Community Land Model is a mechanistic representation of land surface processes as shown here. We couple that within Dart, and we run a traditional ensemble and common filter ranging between 40 and 80 ensemble members. We apply adaptive inflation and localization. We induce spread within CLM ensemble members by introducing atmospheric meteorology reanalysis data. This provides a forecast prior. We update that through the observation and then regress that upon the rest of the model state, providing an improved forecast ensemble. We've applied this to many applications within the Earth system modeling world. We've assimilated in leaf area and biomass observations within the Western United States and also the Arctic and Boreal region, not only improving carbon cycling, but also hydrological cycling and the energy cycle as well. We've also applied this to soil moisture data, improving surface soil moisture simulated through CLM across China, and also the subsurface soil moisture as well. We've also employed this with a MODIS snow cover fraction data. Directions we want to go in, we've currently implemented the ability to simulate in snow water equivalent data. This includes a repartitioning algorithm within Dart, which repartitions the observed SWE into the multiple snow layers as simulated from CLM. Recently, solar-induced fluorescence has been included within CLM, allowing us to assimilate that using Dart. We also have a variety of filters to choose from besides the traditional ensemble and common filter, one that takes into account bounded quantities and limits the adjustment to only physical regions of model space. We've also recently developed a tutorial to increase our user base and improve understanding. Any questions, please go to our website. Thank you.
Hey, I'm Clara Draper from NOAA, and I'm going to be quickly reviewing the Land DA that we use in our current NWP systems, and then what we're planning for the future. So in terms of what we're doing at the moment, in our global system, we're quite far behind what everyone else is doing. In our global system, we have a snow depth analysis based on the assimilation of the snow depth analysis product that's produced by AFWA, the Air Force Weather Agency. This basically consists of taking the snow depth product that they produce, regridding it onto our model grid, QCing it with IMS snow cover observations, and then merging this with the forecast using a really simple rule-based algorithm. We have no soil moisture or soil temperature analysis at the moment, although we do retrospectively correct these states for errors in recent model forecast precipitation using observed precipitation. In our regional system, we have a slightly different snow depth analysis, which is also probably a little much simpler than what's being done elsewhere. And this assimilates only the snow cover observations, no snow depth observations. We have a simple soil moisture and soil temperature analysis in that regional system, which is based on assimilation of atmospheric observations, which includes the screen level observations. In terms of what we're working on developing in the future, so this is being developed for GFS V17, which is scheduled for launch in 2024. We're replacing the snow depth analysis with an OI-based snow analysis, which is based pretty directly on what's being done elsewhere. This system will assimilate station snow depth observations and IMS snow cover. This to date is pretty mature. It's been implemented in JEDI. We've tested it in the atmospheric system with NOAA, which is our current land model and found that it improved snow depth and the atmospheric temperatures. However, as a part of the update to GFS v17, we're also updating our land model. And so I've tested it in land only mode with the new land model NOAA MP and found that it improves the snow depth. And we're just waiting for the GFS to be a bit more mature with NOAA MP before we test that in the atmosphere. I'm also building a new soil moisture and soil temperature analysis using the same DA machinery as is used for the atmospheric DA and assimilating screen level observations initially. The plan is to use a hybrid 4D ENVAR in JEDI. Initial experiments not using JEDI, but using our current system and also using the LETKF, so just the ENKF component of the hybrid system, shows small improvements in 2-meter temperature from the assimilation of the 2-meter observations. And then I'm currently updating this to the atmospheric model with NOAA MP and also implementing the hybrid DA system rather than just using the LETKF component. Yeah, so that's it for now. Thanks, everybody.
Hello, my name is Christina Charlton Perez, and I thank you for the opportunity to talk about land surface data assimilation at the Met Office. I'd just like to recognize my colleagues who I work with in this activity. At the Met Office, our LSDA exists to provide benefit for weather forecasts, and our goal is to improve global and regional forecasts of surface temperature and humidity, so we do not verify against soil moisture observations or snow observations at present, but we welcome benefits in other areas like hydrology, and we have seen benefits in the regional model due to improvements in LSDA. This slide briefly summarizes LSDA activities operationally at the Met Office. Our LSDA is weakly coupled with the atmosphere. The soil moisture and temperature DA uses the same approach across global and regional systems, producing a land analysis at different frequencies of the soil moisture, skin, soil, and snow temperatures, via an SEKF method using an estimated H operator or sensitivity matrix derived from the Joint UK Land Environment Simulator, or JOULES. We assimilate screen data, so pseudo observations of temperature and humidity, and we use the ASCAT soil wetness product. We've recently improved the bias correction of the ASCAT product and implemented some error boosting at extreme values. Please see the link below this for our paper to explain a little bit more about this. Snow DA differs in the global and regional systems in both observations and method. And here's a graphic just to illustrate that weak coupling, how the DA systems, which are independent, produce analyses which are used as the initial runtime, but the background for the next cycle is always the result of a coupled run between the atmosphere and the land. And as I said, atmospheric obs are taken into account in the land DA step, but then the land analyses are used by the coupled model run. What's next for us? We're currently porting our systems over to the new HPC, and we're now preparing LSDA systems to work with a new dynamical core and new infrastructure, or LFRIC, for a cubed sphere grid, which you can see here in the graphic above. So our current model UM is on a lat long grid on the left, and the cubed sphere is on the right. Thank you very much for your time. If there are any questions, please don't hesitate to contact me. Thank you.
Hello, my name's Alex Norton. I'm a postdoc at JPL. I'm going to give a brief insight into the Carbon Data Model Framework called CARDAMOM. CARDAMOM is a Bayesian model data fusion system. It consists of a physical model called DALEC and an adaptive Metropolis-Hastings MCMC algorithm to estimate posterior probabilities of time-invariant parameters and initial conditions. The model is computationally lightweight, allowing for non-linear optimization. There's a range of model structures that can be used with CARDAMOM of varying complexity. Recent model developments include new water cycle processes, aerobic and anaerobic decomposition for CO2 and methane emissions, new climate-driven LAI scheme, new canopy photosynthesis scheme, and a new dynamic plant allocation scheme, as well as an energy balance. Overall, these parsimonious model structures simulate carbon and water states as described by the time-invariant parameters and initial conditions. Some of the observables we've used include flux tower, ET, GPP, and NBE, NBE from airborne atmospheric inversions, solar-induced fluorescence, live biomass, snow cover fraction, and GRACE total water storage. Shown here are some of the current activities. The range of science applications are diverse, from inferring and predicting carbon and water fluxes and states, inferring ecosystem parameters, information content analyses, and comparison of model formulations for key processes. I'll finish up here with some publications listed and a word cloud that we generated from a survey of Cardamom users' active projects. Thank you.